Hi folks, welcome to chemistry. One of the things I want to talk about first is learning how to think about chemistry so that you don't get confused. Sometimes students get overwhelmed by the vocabulary we need to know, as well as the equations and calculations we need to be able to do. And I'm going to ask you to draw particle diagrams, and they don't necessarily see a relationship between all of the different parts that we learn in chemistry. And so I want to assure you that they are related to each other. So I want to talk about what chemistry is and why we're going to study it the way we're studying it. So first of all, chemistry is the study of matter. And matter is just anything that has mass and volume. Mass is just how much stuff is in something. So if you put it on a balance and you see that it has a mass of, an object has a mass of 30 grams, then that's a mass versus volume is how much space something takes up. Chemistry attempts to explain why matter behaves the way it does. So chemistry kind of started because people wanted to explain the world around them. And so this is the phenomena, the things that you can see with your eyes. You don't need special equipment to see it. We're just trying to explain why we see the things that we're seeing. So one of the things that you might notice at a macroscopic level is you might look at table salt and say, hey, why does this salt that I put on my food seem to be making up crystals that seem to be like perfect little cubes? What's the reasoning behind that? And that's something that you can observe with your eyes. And so then we want to tie that to two other kind of levels of understanding. We want to be able to explain what's happening to particles at the microscopic level and also be able to represent what we're seeing using symbols or equations or things like that. So let's look at the microscopic level next. This is where we're explaining what particles are doing to make the macroscopic thing happen. And so this is microscopic. So this is stuff that's too small to see. In fact, we should technically call it submicroscopic because you can't see atoms with a microscope. But still, it's particles that are too small to see. What's happening with these particles? And so in the case of table salt is made up of ions, and we haven't learned about these yet, but you can see here that I've got some particles with positive charge, some particles with a negative charge. And you know from previous science classes that opposite charges attract. So all the negative ions are surrounded by positive ions, all the positive ions are surrounded by negative ions, and you can see that when you make this repeating pattern, you do get a cube shape. And so that kind of explains why, I mean, even if you have a really large chunk of salt, the breakages tend to happen at right angles like you would have with a cube. And so this seems to kind of be an explanation of why little crystals of salt would be cube shaped. So how do we then represent this symbolically? Well, there might be a few different ways to represent what the particles are doing. We could use symbols, we could use equations, we could use diagrams. To represent sodium chloride, table salt, I could just write the formula. It seems that for every one sodium, I have one chlorine. Although that isn't actually chlorine, that's a chloride ion. So for some situations, I might want to actually show you what the ions are. Sodium ions with a positive charge, chloride ions with a negative charge. Or in other situations, I might want an even more detailed model where I'm actually showing you kind of what's happening to electrons in the sodium and in the chlorine. So here you can see that sodium has one valence electron, and it's going to lose that one valence electron to have a positive charge. And chlorine has 7 valence electrons, and it's going to gain the 1 electron from sodium to have 8 valence electrons and a charge of -1. Now, we haven't learned enough about atoms yet to see why this might be happening, but this is another model we might use in certain situations. So you can see that there's a macroscopic level, the phenomenon that we can see that we're trying to explain. The microscopic level is what's actually happening with the particles, and then what symbols or representations do we use to show that? And sometimes there's more than one representation, and the one we choose is just right for the particular situation depending on what we want to show. And so I will try to point out to you as we go throughout the year kind of the relationship between these three, like, hey, this is the macroscopic thing that we see with our eyes. How do we represent this microscopically with particles, and how do we represent this symbolically? So let's do another example here. I just want to make my macroscopic observations. What do I notice? I notice that the Coke Classic is at the bottom of the container. It sank in the water, and the Diet Coke is floating in the water. So I wonder why this might be. That's the observation I can observe. What's happening at the particle level to make this happen? Well, you might not be aware of this, but sugar, it takes a lot of sugar to make Coke sweet. But NutraSweet is actually sweeter per gram. You need less NutraSweet to make something taste sweet than you do sugar. So, in terms of particles, Coke has more mass in the same volume, because it has to have lots of sugar particles in there to make the drink sweet, versus the Diet Coke, where it maybe just needs a few NutraSweet molecules to make it taste sweet. So Coke Classic has more particles crammed into the same, and more mass crammed into the same amount of space as Diet Coke. We can represent this symbolically using an equation. Density equals mass divided by volume. A lot of times people think that objects sink because they are heavy. That is not why they sink. They sink because they are dense. And density takes into account heaviness, takes into account the mass, but also takes into account the volume. And so density is mass divided by volume. And so Coke Classic has more mass in the same amount of volume as Diet Coke does. So this is how we can kind of use, again, we can make observations macroscopically, talk about what's happening at the microscopic level, and then symbolically represent what's going on. So before we move too far ahead, we should talk about particles and what particles are. So particles can mean different things in different situations. Particles could mean atoms or molecules or ions, and so in these pictures here, in this first picture, which is labeled R, this represents atoms. Each atom is separated from other atoms by, white space here, so you can see that each particle is separate to each other, and here each particle is an atom. But in this next picture, labeled RSQ, we have 5 particles. 1, 2, 3, 4, 5. Again, each one separated by white space, but the particles here are molecules, where they're actually 2 atoms joined together. And this particular model is pretty detailed because I'm showing you that each molecule has 2 atoms inside of it. But if the molecule were really big, I might not want to draw every single atom that's in the molecule. So sometimes I might just draw a shape and say, that's a molecule. It's got 15 atoms in it, but I don't feel like drawing all 15 of those atoms. And so people can have more detailed or less detailed representations depending on what exactly they're trying to represent. Here in this example, because we haven't learned about molecules yet, I want to show you that a molecule is made up of more than one atom. So I drew the separate atoms here. In this next picture, I have 8 particles. 1, 2, 3, 4, 5, 6, 7, 8. The thing that separates each particle from each other is there is kind of white space between them to show that they are separate particles. When you have 2 atoms that are chemically bonded together, that's what makes a molecule. So this is all a single particle. Even though it's made up of 2 shapes, those 2 shapes are touching, so they're chemically bonded together and part of the same particle. And so particles can mean a variety of different things in different situations, and we can vary in the amount of detail we show about the particles. So I've said this out loud, but here it is in writing. Sometimes we show smaller parts of in the diagram, we use complex models to show all the small bits inside of a particle, and sometimes we don't. Sometimes we use simple models, and it just depends on what the purpose of the model is. A lot of times when we draw molecules, I'll just represent an atom as though it is a plain sphere. Atoms are more complicated than that, but if all I want you to know is that a molecule is made up of two atoms, this model is perfectly fine for that purpose. Other times, I'm talking about what's happening to something inside of an atom, like what's happening to the electrons, in which case I need a more complex model. I want to actually see what's inside the atom, and so I want to draw the parts that are inside the atom so that we can talk about what's happening to the parts. So in chapter 1, we're going to be focusing mostly on atoms. We'll talk more about molecules and ions later, but we're going to talk about atoms and how we know what we know about them. I hope this helped.